The universe is not expanding. It is tearing, and every galaxy we see is nothing more than a rising ripple on a three-dimensional surface that belongs to a larger, four-dimensional body, a body that is slowly, quietly, and perhaps irreversibly falling apart. If that thought made you stop for even a breath, then press like, share, and subscribe. You will need the momentum, because what we are stepping into is not a new idea. It is a new way of seeing everything you thought space was. Now let us begin. Imagine the universe not as a volume, but as a skin, a boundary, a thin, trembling membrane wrapped around something deeper, a region with an additional spatial dimension. From within this viewpoint, the galaxies are not floating through emptiness. They are perched on the surface of a structure whose interior you cannot enter, but whose stresses you can feel in every curvature of space. The first sign that something is wrong with the traditional picture is expansion. It behaves strangely. It accelerates. It varies by direction. It defies the expectations formed by ordinary matter and ordinary gravity. But under a four-dimensional perspective, none of this is strange. A surface under tension does not expand in a uniform way. It cracks and it pulls. What we call accelerated expansion may simply be the widening of fractures along the three-dimensional boundary. These fractures do not open into empty space. They open into the deeper four-dimensional interior that supports the membrane of the cosmos. Now consider the great cosmic voids, vast regions that contain almost no galaxies, no clusters, no significant matter at all. We treat them as deserts in an otherwise structured universe. But if the cosmos is a surface, then these voids are not empty regions. They are depressions, places where the four-dimensional interior has weakened, allowing the surface to sink. Likewise, the regions rich in galaxies, dense filaments, and nodes of the cosmic web are thickened segments of the membrane, areas where internal tension has caused the surface to bulge outward. If you could somehow step into the fourth spatial dimension and look at the universe from the outside, you would see the cosmic web not as a network of matter, but as a network of stress lines. You would see voids not as emptiness, but as bruises. Every phenomenon we observe becomes a surface effect. Curvature becomes the reaction of the membrane to forces from the interior. Gravitational attraction becomes the surface's attempt to redistribute tension. The bending of light around massive objects becomes not merely a feature of three-dimensional geometry, but the visible trace of a deeper instability beneath us. Then there is the oldest radiance we can measure, the cosmic microwave background. It glows with astonishing uniformity, as though the early universe were a single, smooth, unbroken field. Yet, it contains tiny fluctuations, tiny patches that are slightly hotter or cooler. In the surface model, that ancient glow is the first scar. The first moment when the four-dimensional interior lost equilibrium and the membrane buckled. The temperature variations become the imprint of the first fractures, shallow, microscopic undulations in a still-forming shell. The more deeply we look, the more the signs accumulate. Galaxies drift apart because the membrane is stretching. Their motion accelerates because the decay of the interior speeds the tearing of the surface. Gravitational waves wash across the cosmos, not as ripples through emptiness, but as tremors spreading along the shell of a collapsing four-dimensional body. Quantum fluctuations, those restless flickers that never settle at the smallest scales, may be the membrane's attempt to stabilize itself, to retain its shape while the deeper dimension beneath it shifts and weakens. And all of this leads toward a single, unsettling possibility. The universe does not have an edge in the way we imagine. It has a boundary, but that boundary is not the frontier of space. It is the outermost layer of a higher dimensional structure losing coherence from the inside. We are living on the surface of something larger, and that something larger is changing. If this is true, then the ultimate fate of the cosmos is not a heat death, nor a collapse, nor a tear into infinite expansion. The final moment would be one in which the membrane dissolves, its tension lost, its coherence undone, and the fabric of space ceases to exist along with the last remnants of the surface. But that is far ahead. For now, to understand this strange possibility, we must ask a quieter question. Why does the surface curve at all? And what exactly does that curvature reveal about the structure hiding beneath it? That is where we go next. The surface bends. That is the first thing you would notice if you could step back far enough to see the entire universe, not as empty space, but as a boundary under strain. The bending is subtle when you measure it from the inside. But from the outside, it would look unmistakable. A great three-dimensional shell, curving like a stretched membrane. Curvature has always been treated as a property of space, reacting to mass and energy. But if the universe is a surface, then curvature becomes something else entirely. Not simply a deformation caused by objects within the cosmos, but the visible imprint of forces acting from the dimension beneath the boundary. Imagine pressing your finger from the inside of a balloon toward the outer skin. To someone watching the surface, the membrane curves as if something heavy rested on it. But the pressure is coming from within, not from something lying on the surface itself. Now, imagine the reverse. Pressure coming from outside, from a deeper dimension that touches the membrane differently. From our viewpoint on the surface, we would interpret the curve only through the mathematics of our three-dimensional world. We would see gravitational attraction, orbital paths bending, light rays arcing, but all of it could be the consequence of internal forces. A four-dimensional pull shaping the membrane from the side we cannot reach. This is the subtlety hidden within the most precise observations made from Earth and from the telescopes placed in space. The bending of starlight near a massive object, the warping of time near the event horizon of a collapsed star, the slow drift of galaxies inside clusters. All of these may be surface-level reactions to deeper influences. To us, they look like curvature produced by mass. But to a being who could observe the full four-dimensional structure, they would look like surface tension trying to stabilize itself. Consider the way light behaves around a massive galaxy. In ordinary physics, the path of the photon curves because the presence of mass deforms the geometry of three-dimensional space. But if space is merely the boundary of a higher dimensional structure, then the photon is not moving through an empty arena. It is sliding along a membrane whose shape is determined by whatever shifts within the four-dimensional interior. Every ray of light we observe is following the geometry created by forces we can only detect indirectly. This leads to a deeper tension. If curvature is a surface reaction, then why does it appear so uniform on large scales? Why does the fabric of the universe stretch with such consistency? Despite the chaotic distribution of matter on smaller scales, a membrane under true internal stress does not bend randomly. It flows. It redistributes its tension. It forms gentle gradients where deep forces push unevenly from beneath it. The smoothness of cosmic curvature could be telling us that the four-dimensional interior is not chaotic. It is decaying in a coordinated way, a slow structural collapse that presses outward through every point on the surface at once. This would explain why galaxies cluster into filaments rather than scatter uniformly. A membrane under tension creates channels, stress lines that anchor the surface as deeper instability grows. Matter flows into these lines not because of simple gravitational attraction, but because the surface thickens along regions where internal pressure concentrates. The cosmic web becomes a map of stress, not a map of matter. And the voids, those immense areas where galaxies are absent, become regions where the internal structure has collapsed early, creating dents that spread wider as the deeper dimension continues to weaken. From the surface, we measure the size and shape of these voids, and we interpret them as products of three-dimensional physics. But in the surface model, they are ancient scars, the early signs of a failing interior. The more one follows this line of thought, the more the picture begins to shift. Curvature is not something occurring within space. It is the shape of the space itself, pulled and pressed by a dimension we cannot enter. Gravity is not a force acting inside the universe. It is the universe trying to maintain coherence as its foundation changes beneath it. If this is true, then everything we observe, from the slow orbits of distant stars to the bending of light across millions of light years, is part of a single story, the surface adjusting to the decay of the structure that hosts it. And that raises a quieter, deeper question. If curvature is a reaction, what exactly is the universe reacting to? The answer lies in the concept of tension. not the tension we experience in everyday materials, but four-dimensional tension, a stress that pushes outward or pulls inward across the entire membrane. This tension governs not only curvature, but thickness, and thickness will become the key to understanding why galaxies form where they do, and why their distribution follows patterns that no three-dimensional theory fully explains. The surface thickens in some regions, thins in others, and bulges outward where the internal force is strongest. These changes are subtle from our side, but they shape the large-scale geometry of everything we see. And so we drift toward the next realization, that the universe does not merely bend, it varies in depth, its thickness changing across space like the uneven surface of a drumhead. And that depth, that hidden measure, is what will guide us into the next part of the story. Because to understand why the universe carries the shape it does, we must understand the places where the surface swells, the regions where the membrane thickens into bulges, and how those bulges become the galaxies themselves. Let us go there next, into the rising knots on the surface of a collapsing four-dimensional world. The surface does not simply bend, it thickens, subtly, unevenly, like a membrane whose deeper structure is shifting beneath it, trying to hold its form while tension moves through layers we cannot touch. This quiet variation in depth may be the most overlooked aspect of the cosmos, because from within, thickness does not look like thickness. It looks like gravity. Imagine running your hand across the surface of a drum. Some areas respond softly, others press back with firmness. To your fingertips, the difference feels physical. To the drum, it is structural. The universe behaves in a similar way. Regions where the surface grows denser or more resistant become the locations where galaxies form and gather. This is where matter begins to imitate the behavior of the membrane itself. The thickened portions of the cosmic surface become anchors, pulling dust, gas, and stars toward them. From our internal perspective, we interpret this as gravitational attraction. But in the surface model, gravitational attraction becomes a secondary effect, a visible symptom of a deeper, structural change occurring across the boundary of a four-dimensional object. Here, the cosmic web comes back into view, its filaments stretching like tendons, its nodes swelling like pressure points. Astronomers map these structures and notice a strange consistency. Matter does not gather randomly, nor does it form smooth, spherical distributions. Instead, it flows into elongated threads, sheet-like walls, and tightly bound clusters. These patterns resemble stress networks, structures seen in thin materials placed under uneven internal tension. Cracks do not form uniformly. Thickness does not increase smoothly. Instead, patches thicken where the internal structure demands stability, and the surface creates ridges and spines to compensate. Galaxies rise where the membrane becomes firm, where its depth increases enough to resist the slow decay moving beneath it. This explains one of the greatest puzzles in cosmic structure: why the distribution of galaxies follows a pattern too organized to be random, yet too uneven to be explained by simple gravitational models. If the universe were governed solely by visible matter and the geometry of three-dimensional space, we would expect a different arrangement. Something less deliberate, less patterned, less architectural. Instead, the cosmos gives us architecture. Filaments hundreds of millions of light-years long, walls of galaxies stretching like continental plates, vast, hollow regions that appear carved out rather than collapsed. A surface under tension creates these patterns naturally. It forms networks where thickness increases, along lines of stress. Those thicker lines appear to us as filaments, and at their intersections, where tension piles up and depth becomes greatest, galaxy clusters take shape. Yet even this picture holds a conflict. If the thickened regions of the surface behave like anchors for matter, why do they persist for so long? Why do they remain stable across billions of years, even as the universe continues to stretch? The answer, in this model, lies not in the matter itself, but in the behavior of the membrane. The surface thickens in response to deeper, four-dimensional forces. Those forces decay slowly, but they decay in a pattern. They weaken the interior while also pressing outward, giving the boundary a reason to build ridges of stability. Temporary supports form to maintain its overall coherence. These ridges, thickened and strengthened by internal tension, are the cosmic filaments. The clusters at their intersections are not simply concentrations of matter. They are knots in the membrane, points where the surface must reinforce itself to withstand instability within the deeper structure. Matter flows into these reinforcements because the membrane itself grows denser, and the paths of stars, gas, and light follow the geometry of this depth. Galaxies do not form where matter is abundant. Matter becomes abundant where the surface thickens. This is why the cosmic web is so uniform on massive scales, and yet so chaotic when you descend into smaller structures. Large-scale order arises from the geometry of tension. Small-scale chaos arises from the turbulent responses of matter within the boundary. But if galaxies form where the surface thickens, what happens where the surface thins? What happens at the places where depth fails? That is where the great voids appear, not long after the thickened regions rise, but as early zones where the membrane collapses inward, unable to hold its shape against pressure from the four-dimensional interior. And this introduces the next movement in the story. If the universe is a surface whose thickness varies, then the voids are deeper than emptiness. They are structural failures. They are dents in the membrane, sinking under the weight of a world we cannot enter. And to understand how they came to be, we must look beyond thickness, beyond curvature, and into the early scars that shape the entire cosmic surface. Let us go there next, into the hollows where the surface first gave way. The surface sinks in places, not from the absence of matter, but from the absence of strength. When you drift far enough into the cosmic hollows, the feeling changes. The universe grows thinner, quieter, as though the membrane beneath your feet is folding under a weight you cannot sense, a weight coming from the dimension behind it. The vast cosmic voids are not simply regions where galaxies never formed. They behave more like indentations, zones where the three-dimensional boundary has collapsed inward. Their silence is not emptiness, it is structural failure. To see this clearly, imagine again that the universe is the surface of a four-dimensional body. Where the interior weakens early, the surface loses its ability to hold tension. It thins, it bends inward, it retreats from stability. From within, this looks like a region devoid of galaxies. But from outside, if such a vantage point were possible, you would see shallow basins forming on the membrane, their edges rising as the surrounding surface thickens to compensate. This is consistent with the observations made by astronomical surveys that map the distribution of galaxies across hundreds of millions of light-years. The great voids appear surprisingly smooth, not jagged or chaotic. They look like bowls, gentle curvatures, formed not by random scattering, but by a larger structural influence. This alone invites a question. If voids are merely empty, why do their boundaries line up with filaments so precisely? Why do they form rounded shapes that reflect the overall geometry of space rather than the chaotic distribution of matter? In the surface interpretation, the answer is simple. The membrane bends inward, where the internal four-dimensional tension slackens. It thickens where the tension intensifies. Voids and filaments are opposite reactions to the same deeper cause. But another conflict emerges. If voids represent structural collapse, why do they grow faster than our conventional gravitational models predict? Why do they push surrounding regions outward, as though something beneath them is pulling the surface down while the edges lift higher? The surface model offers a single explanation. The collapse is ongoing. The interior of the four-dimensional structure continues to weaken, and the thinning propagates across the membrane. A void is not a place that failed once. It is a place that keeps failing, slowly drawing the surface inward as the deeper dimension unravels. This continuous collapse aligns with an unsettling observation. The emptiest voids accelerate their expansion relative to the rest of the cosmos. They are not static depressions. They are widening scars. In materials science, a surface under internal decay forms similar features. Regions where the internal lattice breaks first become soft zones. Pressure redistributes, and the surface bends inward, often creating expanding cavities. The same principle may be at work across the universe, scaled to a size that defies imagination. As the void deepens, the edges rise, the filaments swell, and galaxies along the boundary drift outward, not because a mysterious energy pushes them, but because the surface around the void stiffens in an attempt to maintain global coherence. This is why voids appear to repel galaxies. They do not push anything away. They simply fall inward more quickly than the rest of the membrane, and the surrounding surface must rise to compensate. Everything reacts to the structure beneath it. Voids become the earliest witnesses of decay. Filaments become the defensive architecture of the surface. Clusters become anchors at the intersections of tension, and the universe becomes a living record of how the membrane tries to hold together, while the deeper four-dimensional interior slowly loses its stability. If the cosmic surface bears scars this large, then the earliest scar of all, the first great imprint of instability, must lie at the beginning of cosmic time itself. A single echo of the moment the membrane first tried to form, already trembling under the forces inside it. And that ancient echo still surrounds us, filling every direction with a faint glow. To understand the voids fully, to understand why the membrane caves inward where it does, we must turn to that glow, the earliest light we can detect, still carrying the first traces of the surface's birth. Let us go there next, to the oldest scar on the cosmic boundary. The surface remembers pressure. It carries the imprint of every force that rose from the deeper dimension beneath it. Not in bright marks, but in thickness, in firmness, in the quiet way its structure gathers strength. Across the cosmic boundary, there are places where the membrane does not sink or thin. Instead, it rises, as if held from below by something more stable, something that still pushes upward even as other regions fold. These rising places become the homes of galaxies, not because galaxies choose them, but because the surface grows sturdier there, as though the membrane thickens to protect itself against whatever is unraveling inside the four-dimensional body. When astronomers map the large-scale universe, they see sprawling clusters of stars, connected by luminous filaments. They see spirals shimmering like whirlpools of light. They see ancient elliptical forms drifting like massive drops frozen in motion. All of these gather along the same invisible scaffold, a scaffold shaped not by matter, but by depth. To understand this, imagine a stretched sheet that varies in thickness. Where the sheet grows dense, pressure from below meets resistance. Where it is thin, the slightest strain causes a collapse. Matter moves according to this structure, not because the surface tells it where to go, but because the structure shapes the paths matter is allowed to follow. Galaxies form where the boundary becomes supportive. Their stars spin and settle into disks, because the membrane beneath them is reinforced, capable of holding weight for billions of years. Dense regions of the cosmos are not random islands. They are the raised contours of a surface under tension, its thickness betraying the places where the deeper dimension pushes outward most strongly. This perspective illuminates an old riddle. Why do galaxies align along filaments that stretch for hundreds of millions of light years? Why do their shapes, spins, and positions follow patterns too large to be explained by local forces alone? If the surface thickens in lines, paths where the internal pressure organizes itself, then galaxies simply grow where the geometry offers stability. A thickened thread in the membrane becomes a cosmic bridge. A reinforced knot becomes a galaxy cluster. An intersection of these knots becomes a supercluster, its weight held aloft by the densest part of the boundary. Yet, a subtle conflict rises here. If galaxies form where the membrane thickens, should not the thick regions expand or drift apart as the deeper interior decays? Why do these structures display such persistence over unimaginable timescales? The answer lies in the behavior of decaying systems. When the interior of a structure weakens, the outer layer often compensates by growing rigid in specific places, not everywhere, only along the paths that stabilize the whole. These reinforcements appear natural, even inevitable, because the membrane is fighting to preserve its integrity. On a cosmic scale, this translates into lines and clusters that endure. They are not static, but they resist dissolution. Matter flows into them, because the membrane draws matter toward its thickest points. The same way a wound organ can concentrate tissue to maintain shape. The galaxies we admire through telescopes are bright because the surface beneath them has strengthened. Their spirals glow because the membrane gives them a place to turn without falling inward. Their clusters shine because the surface beneath them gathers itself, like hands tightening to keep form. But for every place where the surface reinforces itself, there are other regions where reinforcement never arrived. Regions that drift into collapse, sinking deeper than voids, becoming hollows, where the membrane struggles to hold tension at all. The galaxies mark the strong places, the voids mark the weak, and between them stretches a network that holds the universe together even as the deeper dimension continues its slow descent into instability. Once this pattern becomes clear, another realization begins to emerge. The thickened ridges of the surface behave like the skeleton of the cosmos, but the skeleton itself is changing, shifting under the influence of whatever is unfolding in the four-dimensional interior. And to follow that shift, we must turn our attention to how the membrane distributes tension across enormous distances, how the cosmic web becomes not merely structure, but a record of the forces pressing through the boundary, a record that continues to rearrange itself, with every tremble rising from the unseen dimension below. Across the cosmic surface, a lattice spreads, a quiet architecture so enormous that entire galaxies become small stitches woven into its pattern. It is not carved into the membrane by matter. Matter is only a passenger. The lattice forms because the surface itself must decide where to hold firm, where to bend, and where to surrender to the forces rising from the dimension beneath it. The structure we call the cosmic web is often described as a network of filaments shaped by gravity. But when viewed as part of a boundary surrounding a deeper world, it becomes something more deliberate, more structural, a framework created by distributed tension. Imagine stretching a sheet of fabric over a hollow form. Where the fabric encounters uneven pressure from below, lines of strain form, threads tighten, patterns emerge. These lines are not decorative. They are necessary for the fabric to hold together. As the form beneath it shifts and loses coherence, the universe behaves the same way. The filaments are lines of tension, drawn across the surface to prevent further collapse. Galaxies cling to these lines, not because the lines need galaxies, but because galaxies are the natural gathering of matter on the sturdiest parts of the boundary. The origins of these lines can be sensed in another cosmic mystery. The alignment of galaxies spins across distances far too large for conventional physics to coordinate. How can galaxies millions of light-years apart share similar axes of rotation? Why do their angular momenta echo one another across the void? In the surface model, the answer is simple. They grew along the same tension paths. When the membrane tightens along a line, it creates a direction, a preferred orientation. Matter falling into that line inherits the same orientation. Galaxies forming at different ends of a filament carry the same signature, because the filament itself is the source of the pattern. But this raises a deeper conflict. If the cosmic web is shaped by tension, should these lines not shift or dissolve? As the four-dimensional interior continues to decay, why do they remain coherent? And why do they maintain their geometry, even as galaxies drift outward under the illusion of expansion? The resilience of the filaments suggests something profound. The internal decay is not uniform. It advances unevenly, forcing the membrane to reinforce itself along specific paths. These reinforcements become semi-permanent skeletons, because the membrane must preserve its overall structure, despite the weakening beneath it. The cosmic web is not a static object, but a stabilized response, a long, slow breath held by the membrane to keep itself from tearing. This leads to a striking interpretation. The universe is not simply filled with structure, but is structure. Structure created out of necessity, drawn across a boundary under constant pressure. It is worth imagining how the web behaves from the side we cannot see. In the four-dimensional interior, pressure builds in pockets, slackens in others, and sends slow pulses outward. Those pulses propagate through the membrane as shifts in tension. Where the pressure rises, the membrane thickens. Where it falls, the surface sinks. The resulting network is a compromise, a geometry sculpted to distribute stress as evenly as possible across an unstable foundation. Even gravitational attraction may be a byproduct of this global choreography. Matter flows not towards mass, but toward regions where the surface gathers itself. To stay intact, Gravity becomes less a force and more a tendency for matter to follow the structure the membrane has already written. This interpretation reshapes how we think about motion itself. Galaxies drift along the filaments because the filaments are the safest paths. Clusters anchor at their intersections because those intersections are knots of maximum stability. Superclusters arise in regions where the membrane must support enormous tension to prevent deeper collapse. All of it reflects a single truth. The surface is negotiating with the dimension that holds it. It resists where it can, yields where it must, and maps its struggle across the cosmic web we observe. Once this becomes clear, a new question settles quietly at the edge of thought. What, exactly, is happening inside the four-dimensional interior that forces the boundary to build such intricate stabilizing patterns? A question that leads naturally toward the idea of propagation, the slow movement of decay through the deeper dimension, and how that movement touches every contour of the surface we call the universe. Deep within the unseen dimension, something moves, not with the urgency of falling matter or the violence of collapsing stars, but with a slow, deliberate pulse, a change in the interior that spreads outward until it reaches the boundary we inhabit. The surface feels this movement as a faint shift, a tightening in one region, a loosening in another, as though the very foundation beneath it is breathing unevenly. This interior motion becomes visible to us through a phenomenon we call the acceleration of the universe. Traditional cosmology interprets this acceleration as a mysterious pressure, pushing galaxies apart. But if the universe is the surface of a four-dimensional body, the acceleration is not a push, it is a pull, a gradual unraveling beneath the membrane that forces the surface to stretch. As the deeper structure loses its integrity, imagine a sheet stretched over a hollow form. As the interior begins to collapse or thin, the sheet does not simply sag. It tightens in some places, tears in others, and stretches further where the internal support vanishes. This stretching appears to grow faster with time, because the collapse beneath it accelerates. What appears to us as cosmic acceleration is the surface adjusting to a loss of stability inside the four-dimensional body. But a troubling conflict begins to emerge when we follow this logic. If the interior is weakening, why does the surface not collapse uniformly? Why does the cosmic expansion differ from place to place, as though some regions of the boundary are being pulled harder than others? Observations show that galaxies in certain directions drift faster than in others. The rate of cosmic acceleration varies subtly across the sky. This inconsistency is difficult to reconcile with a perfectly uniform force, yet it makes perfect sense for a surface reacting to an uneven decay. In physical systems, when an interior weakens irregularly, the outer layer stretches in patterns. Some areas thin quickly, others hold firm for a time, and the boundary becomes a map of the collapse beneath it. The cosmic surface behaves the same way. What we interpret as dark energy may be the uneven propagation of decay inside the four-dimensional interior. Where the interior loses coherence more rapidly, the surface stretches faster. Where the interior retains some stability, the rate slows. The universe appears to accelerate because the collapse that drives it moves deeper, pushing outward through the membrane. This interpretation mirrors the way cracks spread through materials. A fracture rarely advances evenly. It wanders, it pulses, it accelerates when the internal lattice breaks suddenly, then slows when the structure resists. The universe may be experiencing something similar, a slow, wandering fracture progressing through a dimension we cannot enter. If the acceleration of cosmic expansion is truly driven by internal decay, then its future becomes clearer. The acceleration will not remain steady. It will change, following the shifting patterns of collapse beneath the surface. Some regions of the cosmos may stretch more violently, others may thicken in response, and the boundary as a whole will continue adjusting to the forces moving within the deeper dimension. This raises another question, one that drifts quietly into place. Once the idea has room to settle, if the surface is stretching because the interior is failing, what happens when the collapse reaches the boundary directly? What happens when the internal structure loses enough coherence that the membrane can no longer reinforce itself? The answer does not arrive sharply. It takes shape like a distant tremor, a sense that the surface is only one layer away from something far more serious. For now, it is enough to notice that the acceleration of the universe may be the first visible sign of a deeper unraveling pushing outward, a signal not of expansion, but of underlying loss. And, as this loss spreads, another phenomenon begins to reveal its true nature, the invisible mass that shapes galaxies and bends light along the surface, a phenomenon that may not be matter at all, but another expression of depth, the membrane thickening under internal strain. That quiet excursion leads us toward the concept we call dark matter, and the possibility that its influence is nothing more than the surface remembering, where it must reinforce itself to survive. There are regions across the cosmic surface where gravity behaves as if there is more mass than the eye can see. Galaxies spin too quickly, clusters hold themselves together with a strength their visible matter cannot explain. Light bends along curves that should not exist. It is as though an unseen substance is adding weight to the cosmos. But weight, in a universe that is only a surface, does not come from invisible particles. It comes from depth. Imagine standing on a membrane that varies in thickness. Where it grows dense, your footing feels heavier, as if the surface beneath you has more presence. Where it grows thin, you feel light, your steps uncertain. The universe behaves in much the same way. What we call dark matter may be nothing more than regions where the cosmic surface thickens in response to forces inside the four-dimensional interior. These thickened patches would influence everything above them. Light would curve more strongly. Galaxies would cling tightly to their centers. Clusters would seem bound by an invisible glue. From within the surface, this would look exactly like mass, but the thickness itself would not shine, would not heat, would not scatter light, because it is not matter, it is structure. In physical materials, a surface can grow denser when pressure beneath it increases. It forms ridges, pockets of reinforcement, places where the outer layer gathers strength. To maintain its shape, these reinforcements behave like extra weight, even though they contain no additional material. If the universe is a membrane, the same principle applies. The surface thickens along the lines of tension that rise from the four-dimensional interior. These reinforcements shape the paths of galaxies and create the illusion of invisible mass. Yet this interpretation carries a conflict. If thickness explains the gravitational effects attributed to dark matter, why does the pattern of these effects stay so consistent? Why do galaxies show similar rotation curves, regardless of their size or composition? Why do clusters bend light in ways that follow familiar patterns across billions of years? The consistency suggests that whatever thickens the surface is not chaotic. It follows the architecture of the cosmic web, forming reinforcements along filaments and nodes, where tension is greatest. This fits elegantly with what observations reveal. Regions that appear rich in dark matter align almost perfectly with the densest structures of the cosmic web. If the web is the skeleton of the membrane, then dark matter is the bone density, the thickness that makes the skeleton capable of supporting the surface. Galaxies forming along these thickened threads inherit the stability of the underlying reinforcement. Their rotations become steady. Their arms and halos settle into shapes that match the geometry of the surface beneath them. Clusters, anchored at intersections of the web, draw strength from the deepest knots in the membrane. Their gravitational influence becomes immense because the boundary beneath them is denser than its surroundings. Even the bending of starlight, one of the earliest clues that dark matter existed, fits smoothly into this interpretation. Light does not curve around invisible particles. It glides along the surface, following the contour of the membrane's depth. Where the thickness increases, light curves more strongly. Where the thickness fades, light straightens. It is the surface, not the matter, that determines the trajectory. This view opens a new question, one that settles quietly across the mind. Once the patterns align, if the thickened regions of the membrane explain the behavior of dark matter, how far does this thickening extend? Does the reinforcement reach deep into the four-dimensional interior, or does it cling only to the boundary? And if the membrane can thicken in some places, can it thin in others, to the point where its structure fails entirely? The thought hangs in the quiet of the cosmic dark, pointing toward the idea that galaxy formation, filament strength, and gravitational stability may be only surface-level expressions of a much deeper transformation underway, a transformation that becomes clearer when we ask how curvature behaves once the membrane reaches its limits, and how the entire cosmic boundary begins to shift shape as the interior continues its slow collapse, a shift that we will feel in the bending of the largest structures the universe has ever carried. Curvature spreads across the cosmic surface like a slow tide, not loud, not abrupt, but steady enough that every structure resting on the membrane feels its pull. From afar, the bending of the universe looks smooth and patient, a gentle sweep across unimaginable distances. Yet beneath this calm, there is a subtler motion, as though the surface itself is responding to impulses coming from a realm deeper than space. In conventional thinking, curvature arises because matter shapes the geometry around it. But if the universe is a boundary, a three-dimensional membrane surrounding a four-dimensional interior, curvature becomes a message, a transmission of whatever is unfolding inside the unseen dimension that supports the cosmic shell. Imagine placing your palm against a thin sheet that covers a hollow chamber. If something inside shifts, even quietly, your hand will feel the sheet stretch, tighten, or sag. The sheet communicates the movement. Because it has no choice, it is the only interface between you and what lies beneath. Space behaves the same way. When the four-dimensional interior changes, the membrane records it. Through curvature, this idea becomes clearer. When examining enormous structures known as superclusters, their shapes do not follow simple gravitational rules. They twist, elongate, and stretch along directions that do not align with the visible distribution of matter. They appear guided by something deeper, as though the membrane beneath them is reshaping itself, and the galaxies above are merely following its contour. A curious conflict appears here. If curvature is governed by mass, then superclusters should form where matter is abundant. But observations reveal supercluster chains in regions where the visible matter is insufficient to explain the geometry. The chains follow paths that trace the deeper tension lines of the membrane itself. The bending does not respond only to matter. It responds to the condition of the boundary. In materials that serve as outer skins or shells, curvature arises from internal stress. Long before the surface tears, the curvature becomes an early warning, a sign that the inner structure is changing texture or density. The same behavior appears on cosmic scales. The universe curves where the four-dimensional interior loses or redistributes its coherence. This interpretation casts familiar phenomena in a new light. The bending of starlight around massive objects may not simply be a reaction to the mass, but part of the membrane flexing to accommodate pressure from below. Galaxies that appear to fall along curved trajectories may be tracing the membrane's shape, rather than a gravitational potential alone. The deeper question emerges quietly. Is curvature a property of the cosmos, or a symptom? This question lingers because curvature appears too organized to arise purely from random distributions of matter. Large-scale maps show enormous arcs, stretching across unimaginable distances, patterns that suggest coordination, not coincidence. If the interior of the four-dimensional body is collapsing unevenly, it would send slow ripples of tension outward through the membrane. Those ripples would not fade quickly. They would shape the boundary for billions of years, carving paths that galaxies would eventually follow, without ever knowing that the true source of their motion is a deeper transformation beneath them. In this view, curvature is not simply the bending of space. It is space responding to the internal reconfiguration of a larger structure. A remarkable implication arises from this. The universe we observe is not isolated. It is coupled intimately to whatever exists within the four-dimensional interior. Every filament, every void, every cluster is shaped not only by matter on the surface, but by movements inside the dimension beneath it. Curvature becomes a bridge between what we can see and what we can never touch. Structures on the boundary slowly rearrange themselves. As the interior continues to lose shape, it is a silent choreography, the surface bending and thickening in response to a world hidden inside it. This understanding brings the story to a turning point. If curvature is a sign of internal change, and if the membrane reshapes itself to maintain stability, then the next question becomes unavoidable. What happens when the interior's decay reaches a depth that the surface can no longer counter? The answer does not strike sharply. It gathers itself slowly, like a shift you sense before you see, an intuition that the stability of the boundary is drawing closer to a threshold, and that threshold begins to reveal itself. In the places where galaxies no longer follow smooth arcs, but twist and distort, as though the membrane beneath them is experiencing something far more turbulent. Those distortions carry us gently toward the realm where the surface begins to struggle, where the boundary's response to the interior turns from quiet adaptation to something more like strain. There are regions where the surface hesitates, places where galaxies do not glide along graceful curves, but twist, stretch, and stagger, as if the ground beneath their paths has shifted in ways they cannot predict. These distortions feel subtle when viewed from afar, yet they whisper of something deeper, a threshold inside the four-dimensional interior that the membrane can no longer calmly absorb. Every boundary has its limit. A surface can bend, it can thicken, it can reinforce itself along lines of tension. But when the forces below grow uneven enough, the outer layer begins to show signs of strain that cannot be smoothed away. Across the cosmic map, astronomers have detected vast patterns where galaxies appear stretched or elongated along specific directions. These distortions are often attributed to the gravitational influence of massive clusters, but some of them do not align with any visible source of mass. Some bend in ways that contradict the expected geometry of three-dimensional space. These irregularities resemble the marks left on a membrane when the interior beneath it shifts abruptly. A change in density, a collapse of support, a pulse of pressure that rises through the surface and leaves the outer layer struggling to maintain coherence. Such pulses could come from zones where the four-dimensional interior is losing structural integrity. As these pockets of instability grow, the membrane above them must distribute the strain to prevent a catastrophic tear. It twists around the disturbance, bending the paths of galaxies as it tries to compensate for the imbalance below. In a physical shell, this would appear as torsion. On the cosmic boundary, it appears as curved arcs, stretched clusters, and misaligned rotations. The distortions are not random. They trace the places where the internal decay becomes most pronounced. Yet, a difficult conflict lingers. If the interior is truly destabilizing, why does the membrane not fail outright? Why does it not collapse? Beneath the overwhelming pressure of an entire dimension losing coherence? Because surfaces rarely surrender all at once. They react with layers of adaptation, thickening in some regions, thinning in others, twisting to redirect stress, and bending to prolong stability. The cosmic membrane is doing the same. Its distortions are not signs of collapse, but signs of resistance, the boundary fighting to remain whole, even as the interior beneath it grows increasingly disordered. This resistance creates patterns that stretch across unimaginable distances. It creates arcs where galaxies drift off expected trajectories and regions where curvature behaves as though shaped by invisible hands. It creates the illusion that gravity is changing, when in reality, the surface itself is shifting to balance forces rising through the fourth dimension. The distortions become a language, a way the membrane communicates the condition of the deeper world. Every twist is a message. Every warped cluster is a signal. Every elongated structure is a thread in a larger narrative, being written by the interior's transformation. These messages accumulate until the boundary begins to reveal a new kind of structure, not filaments formed by tension, nor voids formed by collapse, but regions where the membrane no longer reacts smoothly at all, regions where its behavior turns from graceful adaptation into something closer to trembling. And that trembling carries a meaning of its own. It is the sign that the surface is approaching a transition, a point where its response to the interior is no longer merely mechanical, but becomes something more complex, a struggle between two realities, interlocked by the same boundary. As this realization settles, a deeper question rises through the quiet. If the distortions we see mark the places where the membrane begins to strain, what lies ahead? When the strain accelerates and the four-dimensional interior presses more urgently against its outer shell, the thought drifts gently toward the idea of structural resonance, the stage where a weakening interior and a responsive surface begin to move together, each amplifying the other's instability. A stage where the universe no longer bends softly, but begins to ripple as though echoing the pulse of the dimension hidden beneath it. There comes a moment in any structure where adaptation gives way to resonance, a point where the surface no longer bends merely to accommodate stress, but begins to answer it, echo it, amplify it, as though the entire boundary has become aware of the rhythm inside the deeper dimension. Across the cosmos, there are hints of this resonance. They appear in the way galaxies drift, not only along curved paths, but along curves that shift over time, as if the membrane beneath them is pulsing with slow waves, rising from the four-dimensional interior. These waves are not explosive. They move with the patience of something ancient, pressing outward through a dimension that does not share the rhythm of space. But when they reach the surface, their influence becomes visible as gentle oscillations of curvature, ripples so large that they shape the motions of entire superclusters. In conventional understanding, such motions are often attributed to massive gravitational attractors or concentrations of unseen mass. But many of these regions reveal no adequate source. They drift together as though responding to a call from beneath the membrane. If the interior is weakening unevenly, its collapse would produce pulses, regions of sudden pressure change, followed by periods of slower decay. These pulses would travel outward, fanning across the surface in broad waves of tension. Matter would follow these waves, drawn into their troughs, lifted along their crests. The universe would begin to move in patterns too coordinated for gravity alone to explain. Yet a conflict emerges when we observe these motions more closely. Some structures behave as though the waves are passing beneath them, while others behave as though the waves originate from their own regions. This contradiction hints that the resonance is not global. It is localized, a mixture of interior collapse and surface reaction, woven together in ways that blur their origins. Imagine a drumhead stretched over a hollow chamber. If something inside the chamber shifts and breaks, the drumhead vibrates. But if part of the drumhead has already thinned or weakened, that region vibrates differently, sometimes sounding as though the motion started there, even when it did not. The cosmic membrane is experiencing the same interplay. Some regions vibrate in response to the interior, others in response to their own thinning, and still others in response to distant patches where the membrane has begun to lose coherence. This blended resonance creates motion that is both familiar and strange. Galaxies accelerate in directions that do not align with their gravitational landscapes. Giant walls of matter shift as unified bodies. The cosmic web breathes, as though the universe has begun to move in long, slow chords. The resonance becomes a kind of language, a conversation between the interior and the surface, each answering the other, in vibrations that span billions of years. What makes this even more striking is the way these motions scale with distance. The farther one looks, the more the resonance dominates, as though the deepest notes of the interior's collapse are carried most clearly across the widest parts of the membrane. This is not how gravity behaves. Gravity weakens with distance, but resonance spreads. The universe is shifting toward a state where the surface is no longer simply reacting, but entering into a feedback with the interior beneath it. And feedback is always a threshold. Once crossed, the motions of the surface and the pulses of the deeper dimension begin to merge shape with cause, memory with event, reaction with origin. At this stage, the membrane's texture becomes critical. Its thickness, its curvature, its regions of strength and weakness dictate how it vibrates, how it carries tension, how it absorbs or amplifies decay. Every reinforcement and every thinning begins to matter more than ever before. And as the vibrations grow, they reveal something else, a signature baked into the surface, a relic from the earliest moments of the membrane's birth that still influences how resonance spreads today, a signature we have already seen, but whose meaning has not yet been fully understood. It is time to follow that imprint to the places where the ancient texture guides the universe's most recent motions, as though the first scars of the surface still whisper instructions to the cosmos it became. The surface carries an ancient texture, a faint, mottled pattern etched into the cosmos long before galaxies formed or light found its way through the dark. This texture is delicate, spread evenly across the sky, like a thin frost on glass, yet within its faint unevenness lies a memory of how the universe first learned to hold itself together. The glow that reveals this texture is not bright to the eye, but it fills every direction with a quiet uniformity. Embedded in that uniform field are subtle differences, slight rises, gentle dips, whispers of warmth and cold, that tell of the membrane's earliest struggles to balance the forces pressing through it. From the four-dimensional interior, this ancient pattern guides more than memory. It shapes the universe's behavior even now. Regions where the early surface was slightly thicker grew into the hubs of galaxies. Regions where the surface was thinner became the seeds of future voids. The cosmic web that threads across the boundary still follows the imprint left by those first delicate ripples of tension. Yet as astronomers map this ancient texture with ever greater precision, they uncover something unsettling. The pattern is not as random as three-dimensional physics would predict. Certain large-scale features align, stretching across the sky, as though the universe inherited a direction, a preference, a faint memory of stress that was not evenly distributed. Some regions of the sky appear subtly colder, others warmer, in ways that trace arcs, larger than any structure formed since the birth of the cosmos. These imprints behave like the remnants of a deeper motion, a tremor from the interior, caught in the surface before the membrane had finished forming. A conflict emerges from this. If the early universe were governed solely by three-dimensional physics, its oldest glow should show a balance free from orientation or design. Instead, it carries hints of a deeper structure, as though the four-dimensional interior influenced the membrane even before stability had emerged. This interpretation suggests something profound. The earliest texture of the surface is not only a record of past tension, but a blueprint, a set of guiding lines that still directs how the membrane responds to the interior's decay today. Imagine a sheet marked by faint ridges. As stress builds beneath it, the sheet is more likely to bend along those ridges, to use the old lines of weakness or strength to direct new movement. The cosmos behaves the same. The ancient texture becomes a network of preferred paths for resonance, for curvature, for collapse. These primordial contours shape the modern universe in ways subtle but persistent. They influence the direction in which superclusters drift, the angles at which filaments stretch, and the boundaries where voids swell and deepen. In a sense, the universe is still following the earliest instructions written upon it, a quiet inheritance from the first moments of the membrane's existence. This raises a deeper question, one that sits softly, just beneath awareness. If the surface still carries the imprints of its origin, what does that imply about the state of the interior that created those imprints? The texture suggests not a smooth, homogeneous beginning, but an interior already in motion, already uneven, already straining. And if the interior was unstable at birth, then its current state after billions of years of slow collapse, must be far more complex, with pressures that shift and deepen in ways the surface can no longer compensate smoothly. That realization invites the mind toward a darker possibility, that the early texture we see is only the faintest shadow of a much larger pattern of decay that has been advancing inward all this time, a pattern that is beginning to reveal itself in the largest structures of the cosmos, not as subtle ripples, but as sweeping distortions that mark the membrane's effort to withstand a force it can no longer ignore. And it is toward those vast distortions that the surface slowly guides our attention, one quiet wave at a time. Across the largest scales of the cosmos, patterns emerge that defy the simplicity of three-dimensional geometry. Superclusters stretch like rivers, flowing in directions that ignore the distribution of matter. Walls of galaxies bend, as if shaped by a hand that pressed against the membrane from beneath, leaving curves that do not match the map of visible mass. These vast distortions are not gentle variations, like the ancient texture imprinted at the universe's birth. They are sweeping, deliberate arcs, movements too coordinated to be guided by the gravitational pull of objects scattered across the surface. They look like the reaction of a boundary that is being pushed unevenly by something deeper. The four-dimensional interior, slowly losing coherence, does not collapse uniformly. Its weakening propagates through pockets and layers, creating zones of pressure that rise toward the membrane, like deep currents pushing upward through a flexible shell. When these currents reach the boundary, they do not merely curve the surface, they reshape the grandest structures built upon it. In cosmic maps, these distortions appear as chain-like formations, where galaxies drift in the same improbable direction, as though responding to a force no observer can locate. Some regions accelerate, others slow, turning the cosmic web into a vast tapestry of motion, guided by pressure lines rather than gravitational centers. The conflict becomes clear when astronomers attempt to explain these flows as the influence of extremely massive regions. Their predictions require enormous concentrations of matter, but when the telescopes look, the mass is not there. The galaxies move, as if they are following a deeper geometry, one written into the surface by forces rising from the interior. On a physical membrane, this behavior appears near the onset of structural failure. As the interior destabilizes, waves of tension propagate outward, and the outer layer bends in wide, sweeping motions. To maintain equilibrium, each wave travels slowly, reshaping the surface without requiring localized pressure points. The entire structure begins to behave as a single, responsive sheet. The universe appears to be reaching a similar stage. The largest distortions mirror these long wavelength waves, not chaotic, not violent, but deeply coordinated, as though the membrane is redistributing tension across its widest expanses. These motions reveal that the cosmic surface has begun to enter a phase where its responses are no longer confined to local regions. The boundary acts as a whole, reshaping itself to compensate for the interior's uneven collapse. This shift marks a transition in the relationship between the surface and the dimension beneath it. Instead of isolated reactions, the membrane moves with a unified rhythm, a slow synchronization between collapse and response. Such synchronization is both stabilizing and troubling. It allows the surface to preserve itself for longer, but it also means that the decay inside the four-dimensional body has reached a depth where its influence can no longer be contained. The largest structures of the cosmos are beginning to echo the shape of the instability within. Once this stage is reached, the membrane faces a new challenge. The regions of greatest thickness and the regions of greatest weakness do not merely respond to internal pressure, they begin to interact through the surface itself. Thickness draws tension, thinness releases it, and across the vast stretches of the cosmic web, the interplay between thick and thin begins to reveal a deeper pattern, a pathway through which the boundary tries to hold its form, even as the interior continues to dissolve. The surface becomes less like a stable shell and more like a living structure, balancing its own strength against the collapse below. And as this delicate balance evolves, the first hints of strain grow into something more pronounced, a quiet shift from curvature and resonance toward outright deformation, a stage where the membrane must decide where to give way and where to reinforce itself. As the deeper decay accelerates, a stage that brings the cosmos closer to understanding how a universe shaped by a surface responds when that surface is no longer enough. There are places where the surface feels fragile, not merely bent, not merely stretched, but almost translucent, as though the membrane has thinned to the point where the deeper dimension presses close enough that its presence hums beneath your feet. These thin regions do not appear as voids or hollows alone. They extend across vast, subtle gradients where the cosmic membrane no longer holds the same firmness that supports galaxies and filaments. They form faint planes where structure weakens, where tension does not gather, where the universe feels one layer closer to its hidden interior. Thinning is a natural consequence of internal collapse. When the four-dimensional body beneath the surface loses density, the boundary above it cannot maintain its thickness everywhere. It grows uneven, thick where it must resist, thin where its support erodes. Galaxies sense this thinning in ways they cannot name. Their paths loosen, their rotations falter, their shapes drift into twisted distortions, as though the surface beneath them is no longer holding a steady contour. Even light behaves differently, gliding along shallower curves, slipping through regions where the membrane no longer offers the same structured resistance. At the scale of the cosmic web, these thinning zones feel like quiet stains spreading across a shell, absorbing tension. Instead of carrying it, they do not gather matter, they release it. And the surrounding filaments must work harder to maintain balance. This leads to a striking realization. The universe is becoming patchy, not in its matter, but in its capacity to maintain shape. The membrane is no longer uniform. Some regions reinforce, others drain. The surface grows uneven as the interiors collapse, advances in layered waves. This unevenness introduces a deeper conflict. If thinning continues unchecked, why has the membrane not ruptured? Why does space still hold, even in regions where its depth falls dangerously low? The answer lies in the membrane's instinct to redirect tension. A weakening boundary pushes stress towards stronger regions, forcing filaments to thicken and clusters to carry more weight. The universe becomes a redistribution machine, a surface that rearranges its own geometry. To prevent failure, this redistribution becomes visible as certain regions of the cosmic web grow denser and brighter, while others drift toward emptiness. The surface is not collapsing evenly. It is choosing where to survive. But such choices come with consequences. As some regions strengthen, others weaken further, creating ever deeper gradients of thickness and tension. These gradients distort the trajectories of galaxies, stretching them into elongated streams that trace the boundaries between firm and fragile zones. In a physical shell, this behavior marks the approach of a critical transition, a stage where the boundary begins to separate into domains, each responding differently to the pressure within. The once unified surface splits into regions of resilience and regions of surrender. The universe reflects this shift. Parts of the membrane still hold the intricate architecture of the cosmic web, while others fade into near structureless planes, where galaxies drift with little guidance. The balance between these zones grows more delicate with each passing epoch. As the interior decays further, the thinning regions will spread, moving like slow, dark tides across the surface. Filaments will tighten around their densest knots in an attempt to compensate, but the pressure placed upon them will grow immense. This interplay hints at an approaching stage where the membrane's effort to survive begins to change character, from quiet adaptation to something closer to struggle, a state where the boundary must stretch itself in ways that reshape the entire cosmos. The surface is reaching a point where reinforcement alone is not enough. It must collapse in some places to preserve others. It must allow thinning so that thickness can concentrate. It must let go in order to hold. And in that letting go, a new pattern begins to form, a pattern that reveals how the boundary will behave as the interiors collapse, approaches deeper layers, a pattern that begins to signal how the universe prepares itself for what comes after resilience, after thickening, after thinning, the stage where the membrane must reckon with instability, spreading through its entire depth, a stage where the cosmos begins to show the earliest shapes of its long descent. There are depths beneath the surface where light cannot reach, and geometry loses its familiar shape. If the universe is truly the boundary of a four-dimensional body, then these depths form layers, hidden strata of instability, slipping further into collapse. As time moves forward, the membrane receives only echoes of what unfolds inside this unseen dimension. But those echoes can be felt in the way the surface struggles to keep its form. The thinning regions widen, the thickened ridges tighten, the cosmic web begins to stretch, not only across space, but across differences in depth, as the boundary attempts to distribute pressure from far beneath. To imagine these layers, picture a vast, porous interior, where support weakens unevenly. Some regions fall inward more rapidly, others resist for a time. Before losing coherence, these variations ripple outward until they reach the surface as gradients of tension and release. Unlike the early motions that shaped galaxies and filaments, these deeper waves carry a heavier tone. They do not simply bend the membrane, they press against it with the weight of structural loss. Where the interior collapses slowly, the surface bends gently. Where the collapse deepens abruptly, the surface tightens, as though bracing for an impact. It knows it cannot fully resist. This uneven interior introduces a profound conflict. If the collapse beneath the membrane is accelerating, why does the surface not disintegrate? What prevents the boundary from yielding entirely to the weakening of the deeper dimension? The answer lies in the nature of boundaries. A surface often survives, not because the interior is stable, but because the boundary is capable of channeling stress. Across vast distances, it redistributes tension to prolong its existence. Yet this process has limits. Beyond a certain threshold, redistribution becomes distortion, and distortion becomes strain. The universe is entering that threshold. Distortions across supercluster scales are no longer gentle curves. They are shifting gradients, broad sweeps through which the boundary attempts to brace itself against the deeper forces pressing upward. These gradients influence every structure resting upon the membrane. Galaxies alter their trajectories as though feeling a soft drag. From beneath the surface, filaments grow thicker, where tension must be absorbed, and thinner, where the boundary can no longer support resistance. Voids deepen as the interior collapses under their regions. More rapidly than the rest, the membrane still holds, but its responses grow more coordinated, more global. Instead of isolated adaptations, the entire surface begins to shift in broad swaths, as though following a single instruction, imprinted by the interior's decay. This coordinated movement marks a change in how the boundary communicates with the deeper dimension. Early in the universe's history, the surface responded passively, absorbing fluctuations without participating in their rhythm. Now, the membrane answers every shift with a shift of its own, mirroring the movement beneath it. This mirroring suggests a coupling, a stage in which the surface can no longer isolate itself from the interior's instability. It moves in unison, echoing the collapse, as if the two worlds are beginning to blur. Such coupling appears in materials approaching structural failure. The shell begins to adopt the same rhythm as the inner lattice until the two behave as one trembling body. The universe shows signs of approaching this state. Large-scale patterns become synchronized. Regions far apart respond with similar distortions. Boundaries between thick and thin regions sharpen as though the membrane is preparing for a decisive shift in how it carries tension. This change does not bring rupture, but something quieter, more intricate, a reorganization of the surface into domains of stability and instability, each shaped by the pressure of the deeper collapse. And as these domains form, they begin to hint at how the membrane will behave when the interior's collapse presses even closer toward the boundary, a behavior that becomes clearer when the thinning regions begin to merge, creating pathways through which tension escapes and through which the surface reveals what lies beneath. These pathways mark the earliest stages of a more profound transformation, a shift in the membrane from a unified shell to a patchwork of zones struggling to share the same collapsing world. Across the thinning regions of the cosmic surface, something unexpected begins to form. Not cracks, not breaks, but pathways, soft channels where tension seeps away, where pressure from the four-dimensional interior finds the least resistance. These pathways do not appear suddenly. They emerge gradually as faint shadows in the structure of space, like subtle depressions in a sheet, stretched too tightly for too long. As they grow, the membrane shifts its burden. Tension that once flowed across the entire surface begins to funnel into these paths. They become conduits, routes along which the boundary can discharge stress that would otherwise tear it apart. In cosmic maps, these pathways correspond to the most extended voids, not simple hollows, but deepening corridors through which the membrane releases the weight of the interior's collapse. The voids lengthen, joining one another, gradually forming networks that mirror the filaments, but in reverse, a dark, inverted web, marking the fragile corridors of a universe trying to protect itself. The existence of these pathways introduces a striking contrast. While the thickened filaments hold the cosmic structure together, the thinning corridors allow the membrane to continue surviving. By giving tension a place to flow, the surface is no longer a single cohesive shell. It becomes a dynamic system of reinforcement and release. Yet, this adaptation brings with it a profound conflict. If the pathways allow tension to escape, why do they not relieve enough stress to stabilize the membrane? Why does the thinning continue? Despite the surface offering new channels for pressure, the answer lies in the nature of the collapse beneath. The four-dimensional interior is not simply weakening, it is unraveling, losing its cohesion in a way that deepens with every passing epoch. The surface can redirect tension, but it cannot stop the source of the tension itself. So the pathways widen. What began as narrow corridors grow into sweeping expanses where galaxies no longer form and the cosmic web no longer holds shape. These stretches of deepening thinness behave like slowly opening wounds, the membrane's quiet concession to the forces pressing upward from the failing interior. Despite this, the surface does not yield entirely. It strengthens its thickest regions, pulls matter into the densest filaments, and braces itself against the pressure rising beneath. The boundary becomes a system of strategic endurance, sacrifice in some places, to preserve stability in others. This process mirrors what happens in stressed materials. A shell that cannot resist pressure everywhere forms channels of weakness to keep the rest intact. The membrane responds in the same way, shedding structure in its most vulnerable regions to maintain the architecture of the whole. Through these pathways, the surface also reveals something else, glimpses of deeper instability, moving closer to the boundary. As the interior collapses further, the pressure changes, become more pronounced, and the membrane must decide repeatedly where to hold and where to yield. This decision shapes the cosmic landscape in ways that grow more dramatic with time. Some voids begin to expand at rates that outpace the rest of the universe, as though the thinning beneath them has accelerated. Other regions, previously stable, start to drift toward collapse as the interior beneath them reaches new stages of decay. These changes hint at a future where the membrane will no longer respond gently to the inner collapse, but will face a more direct confrontation with what lies beneath. A stage where tension no longer flows smoothly through pathways, but rises sharply toward the surface itself. That rising pressure creates the conditions for a new behavior of the boundary, a behavior in which collapse spreads upward through the membrane, changing its shape in sweeping, decisive motions, a behavior that brings the cosmic surface into the early geometry of dissolution. There comes a point when pressure no longer whispers through the membrane. It rises, steady at first, like a tide pushing against a shore, and then deeper, a surge from the four-dimensional interior that the surface can no longer guide quietly. Through thinning pathways, the movements that once spread gently across the boundary become broader, heavier strokes. The membrane, strained for ages, begins to shift in sweeping motions, as though entire regions of the cosmos are being pressed outward by the weight of a collapsing world beneath. At this stage, the behavior of the surface changes. It no longer bends only along filaments or collapses only within voids. Instead, vast portions of the boundary respond as unified plates, continents of space, tilting, stretching, and drifting along gradients of tension that reach upward. From the deeper dimension, these sweeping motions become visible in the way superclusters start to move, not individually, but in coordinated arcs, almost as if the boundaries of entire cosmic regions are sliding over the membrane of a trembling four-dimensional core. Observations reveal that certain enormous structures accelerate in shared directions, despite lacking the mass to pull one another. Their motion feels guided, not by matter, but by shape. This shape belongs to the membrane, a shape that is changing more rapidly as the interior continues to lose support. Yet a profound conflict forms here. If the interior beneath the surface is collapsing with increasing force, why has the membrane not ruptured? Why does space not shatter under the rising pressure of the deep dimensions dissolution? Because the membrane has entered a state of large-scale reorganization. Surfaces approaching their limit often move as unified bodies, allowing stress to pass through them in waves that preserve the whole, at the expense of local distortions. The boundary of the cosmos is behaving the same way. It is no longer distributing tension as an evenly curved shell, but as a set of vast zones sliding into new configurations as they brace against the next stages of collapse. This global shifting reshapes the cosmic landscape. Regions once stable begin to stretch toward one another, as though drawn by invisible slopes forming beneath the membrane. Void corridors widen as the thinning regions merge into deeper tracks. Filaments tighten into elongated strands as the surface pulls matter toward its strongest reinforcements. The universe begins to resemble a landscape under slow subsidence, a terrain adjusting to a foundation that is sinking unevenly. This stage marks the early geometry of dissolution, not catastrophic, not sudden, but unmistakably directional, a movement in which the cosmic boundary leans toward collapse, even as it strives to maintain its coherent shape. In the physics of shells and membranes, such large-scale shifts signal that failure is no longer a distant possibility, but a forming trajectory. The surface reorganizes to delay the inevitable, but each motion becomes a preparation for what follows. On cosmic scales, this preparation appears as a tightening of the strongest filaments and the deepening of the most fragile voids. The universe is stabilizing itself, not through balance, but through contrast, concentrating structure where it can and releasing it where it must. The deeper interior continues its collapse, and the boundary feels the increasing closeness of what lies below. Pressure rises until the membrane's response shifts again from broad reorganization to a more direct engagement with the collapsing core. That engagement is not quiet. It shapes the universe with motions that feel less like adaptation and more like surrender. a stage where the boundary begins to show the first clear outlines of how dissolution will one day complete itself. And along those outlines, the cosmos prepares for the final return to the central idea that has guided this entire journey. A universe that was never a space, but a surface, living on the edge of a deeper world's unraveling. There is a quiet moment, almost imperceptible, when the vast motions of the cosmic surface begin to echo something familiar, a rhythm, a curvature, a slow leaning of the membrane that recalls the earliest idea we first touched at the beginning. The universe is not a space, but a boundary, a surface shaped by the fate of a four-dimensional world that has been dissolving from the inside out. As the interior sinks deeper into collapse, the boundary reacts in ways that feel increasingly reminiscent of its earliest behavior, long before galaxies formed, before filaments appeared, before light had room to travel. The newborn membrane responded to internal pressure with a mixture of tension and surrender, thickening in some places, thinning in others, seeking any shape that might hold. Now, billions of years later, those same patterns begin to re-emerge. The surface bends along sweeping arcs that mirror the primordial contours etched into the cosmic texture. Voids deepen into the same corridors, shaped by ancient thinness. Filaments stretch along the ridges that once stabilized the first trembling moments of the boundary's existence. The universe does not return to its beginning, yet it moves in a way that acknowledges that beginning, as though the membrane, under immense pressure, remembers the shape that first allowed it to survive. This return carries a profound conflict. If the surface is following the imprint of its birth, does this mean that the earliest pattern was itself a response to an even older stage of internal collapse? Has the four-dimensional interior always been in motion, always shifting, always decaying, long before the membrane formed around it? If so, then the universe has never been stable. The surface was born into the struggle of another world's dissolution, and the cosmic architecture we observe is merely the long echo of that deeper unraveling. This possibility adds a new layer to the behavior we see today. The membrane's large-scale motions, the sweeping drifts of superclusters, the widening pathways of thinning, the tightening of reinforced ridges, are not only reactions to current instability, they are reenactments, reflections of a pattern the boundary has known. Since its first breath, materials under extreme stress often revisit their earliest shapes as they approach structural failure. A shell that once bent into a particular curve during formation tends to fold along that same curve. When it can no longer resist tension, the cosmos may be doing the same, returning to the contours that allowed the surface to exist in the first place. This return is not a collapse, not yet. It is an alignment, a reorientation of the membrane, as the interior's pressure presses closer to the boundary than ever before. Galaxies follow these emerging contours without recognizing their meaning. They drift along curves, older than themselves, curves traced by the earliest variations. In the membrane's thickness, clusters gather at the same kinds of knots where the first reinforcements once formed. Even the vast voids seem to inhale the memory of primordial collapse. The universe is not falling apart chaotically. It is returning, not in time, but in behavior. It is folding into the patterns that have defined its structure since the beginning. This return reveals something else. The boundary struggle is approaching a stage where the surface and the interior are intertwined so deeply that neither can move without shaping the other. The membrane no longer reacts. From a distance, it feels the collapse as though it were its own, and in that closeness, the universe approaches the threshold between endurance and dissolution, a threshold that quietly prepares the mind for the final descent, not into destruction, but into the last, soft understanding of what it means for a surface to hold its shape as the world beneath it finally lets go. A threshold, waiting in the calm that follows, where the cosmos begins to dim into the quiet of its final chapter. There is a quiet that arrives when a structure reaches its final equilibrium, not balance, but acceptance. The cosmic surface, after ages of bending, thickening, thinning, and reshaping itself to withstand the collapse beneath it, enters a state where motion becomes gentle again, not because the pressure has faded, but because the membrane has surrendered the idea of holding the universe together forever. If the cosmos is the boundary of a dissolving four-dimensional body, then the final stage is neither violent nor sudden. It is a soft dimming, a slow release of the tension that once defined everything. The surface loosens its grip on the patterns it has carried since the earliest scars of existence and begins to drift toward a form that reflects the interior's last breath. In this late stage, the distinctions that shape the universe start to blur. Filaments lose their sharp edges. Clusters sink deeper into the geometry of the membrane. Voids widen until their boundaries are no longer boundaries at all. The cosmic web, that intricate scaffold that once held galaxies in place, fades into a softer topology, a memory of structure rather than structure itself. The membrane becomes smooth again, but not like it was in its youth. The smoothness now is the smoothness of surrender, a surface no longer resisting the weight of the collapsing interior. This transformation does not erase the universe, it releases it. The boundary stretches just enough that the final remnants of structure glide apart, not hurried, not forced, but carried by the same quiet pressure that once shaped the first stars. In physical systems, a dissolving surface enters a stage where every point on it feels the same subtle tug from what lies beneath. Differences blur, contours relax. The shell becomes a single, unified whisper before it disappears. Across the cosmos, a similar whisper rises. Galaxies no longer drift along defined paths. They fall into slower, softer arcs. As the membrane evens out, light spreads without meeting sharp curvature. Space becomes less of a shape and more of a feeling. What remains is the essence of the boundary, a thin, luminous quiet, floating above the last traces of the four-dimensional interior. Even the deepest forces that govern the universe grow faint. Gravity weakens as structure dissolves. Curvature relaxes as the membrane thins. The cosmic texture fades into a near-perfect stillness, the kind that resembles a final exhale, and beyond that stillness lies only the question that has followed us from the first chapter to this one. If the universe was never a space, but the surface of a deeper world, what becomes of a surface? When the world beneath it finally falls away, there is no answer, only the gentle narrowing of boundaries, the soft folding of the membrane, the drifting release of the last patterns that once formed stars and light. In that quiet dissolution, the cosmos does not end. It simply stops holding shape. What remains afterward is not darkness nor silence, but the absence of tension itself, a return to whatever lies beyond, a surface that has forgotten how to be a surface. Close your eyes. The boundary loosens, the deep dimension exhales, and the universe continues its soft, inevitable unfolding.